Okay, so I guess welcome to week 8 of the senior stream. So, in case you weren't here last week, we did a bit of the dynamic programming review on mostly just the theoretical parts of dynamic programming. And you can find this document in the senior tab here. So, you'll find a link to the Google Docs here. I do apologize. I forgot to hit record last week, so there was no video. But it wasn't a very long lesson anyways. So to give a quick summary, the most important part of this whole document is the components of a dynamic programming solution. And so there's your state, your base case, and your transition. So this is the most important thing as we're going to be going along at today's problems. And so today we're going to be talking about prefix-based DP. And this is going to be one of the most common forms of dynamic programming that you'll encounter in competitive programming. And so prefix-based DP refers to dynamic programming where each state is defined by a prefix. And so DP at I corresponds to indices 1 to I. And by corresponds, I mean it's related to the prefix that's ending at I. And so we would access the states by usually iterating from left to right and updating DP at I using some subset of DP at j for all j is smaller than I. And what I mean by this is we're going to update the DP states from left to right, and we're going to update each of the current states by the states that we already processed, also known as the states on the left to the left of it. Okay, so for our first example, realize that we've actually already done this kind of DP before by constructing our prefix sum array. And so recall that the prefix sum array for DP at I, or I used to call it PSA at I, it doesn't matter what it's called, but DP at I would store the sum of all A of j for every j from 1 to I, right? And so in other words, DP at I would store the sum of the prefix. And the transition when we went ahead and constructed the prefix sum array was DP at I equals DP at I minus 1 plus A at I, right? And so this would help us calculate DP at I in O of 1 time every time we went through it. And so the construction of the prefix sum array is actually an example of prefix-based DP. And so for our second example here, we're going to be looking at this problem. So it says Taro's summer vacation starts tomorrow, and he has decided to make plans for it now. The vacation consists of n days. For each I from 1 to n, Taro will choose one of the following activities and do it on the ith day. So activity A, that's swimming in the sea, and he'll gain AI points of happiness. Activity B, catch bugs, he gains BI points of happiness. And activity C, which is do homework, he'll gain C points of happiness. And so this is an important part of the problem, which says that he cannot do the same activity for 2 or more consecutive days. And so it wants you to find the maximum possible total points of happiness that Taro gains. And so as we go along each day, we want to know the maximum happiness he can have for some subset of the first I days, right? So if we were to let DP at I store the maximum happiness he can have after the first I days, but here's where the part where he can't do the same activity for 2 or more days comes in. So say I wanted to calculate DP at I would know DP at I minus 1 because I've already pre-calculated it in our previous iterations, right? So if I know the maximum happiness from the first I minus 1 days, for the ith day, if I were to choose from activity A, B, or C, there's no way to tell what he did on day I minus 1, right? And so if on day I minus 1, he chose activity A and obtained the maximum happiness that is stored in DP at I minus 1, then DP at I, if DP at I chooses activity A again for day I, then that would be invalid. And so you can see that there's no way to tell what he did on day I minus 1 if we just have the dimension as dp at I. And so this is where we want to add an additional dimension to store the condition, right? So instead, our dp state is going to be dp at ij, storing the maximum happiness he can have after the first I days, where j represents the activity he did on the ith day. And so we don't have indices as a, b, and c, so we're just going to let 0 represent activity A, we're going to let 1 represent activity B, and we're going to let 2 represent activity C. And so our transition is now this. So dp at I at 0 stores the maximum happiness he can have on the first I days if he chooses activity A on the ith day, right? And so on the I minus day, he must have chosen activity B or C. And he'll add on the happiness he gets by choosing activity A on day I. And so we'll take the maximum between choosing activity B and choosing activity C on the I minus 1 day, or on day I minus 1, and then add on the value that add on the happiness he gets if he chooses activity A. dp at I at 1, that just corresponds to the maximum happiness he gets from the first I days if he chooses activity B on the ith day. And so by a very similar logic, we're going to choose the maximum between choosing activity A and activity C on the I minus 1 day. And that's because we can't have activity B if we're going to choose activity B on the ith day, right? We can't have two activities that are the same consecutively. And we're going to add on the happiness he gets if he chooses activity B on the ith day. And for C, that's the exact same process. And so in the end, we're going to end up with 3 dp values, and that's dp of n at 0, dp of n at 1, and dp at n at 2. And so that's what that stores is the maximum happiness he can get for all 3 days, for all n days. Either he chooses A, B, or C on the nth day. And so if we just take the maximum between these, we'll have the right answer, right? And so let's go ahead and implement this. So when you're doing a DP problem, first of all, you need an array to store all of your variables, but also you'll need a DP array with exactly how you defined it, right? So let's first declare the values of A, B, and C, so the arrays A, B, and C, and we can see that n goes up to 10 to the 5. And for our second dimension in our DP array, we said that the j value would be either 0, 1, or 2. And so we can just make that second dimension 3 there, and that'll be big enough. Okay, and we'll just take in input of n, and then take in input of A, B, and C on each line. Okay, and one thing I didn't talk about here is the base case. So what would be the base case of my problem here if my state is dp at ij storing the maximum happiness he can have after the first I days, where j represents the activity he did on the ith day? Yes, dp at 0 would store the base case, and what would that be equal to? Okay, sure. Uh, okay, so I've actually one indexed my array instead of um. Okay, that would be correct. But yeah, I've one indexed my arrays, so I'm gonna do this slightly differently. So I'm gonna let DP at 0, DP at 0 at 1, and DP at 0 at 2 to all be 0, because after the first 0 days, I'm going to have um, I'm gonna have 0 happiness, right? Because the 0 days have passed, and so whoops. And by the way, this statement is actually redundant because it's going to initialize all my values to 0 anyways, but I just wanted to show the base case here. And so after 0 days, um, the happiness is 0. And that's no matter what activity you choose. And so let's implement our transition here. And so we have 3 cases, right? So maybe I can just copy paste this. I'll need to write a for loop. Okay, so this is for choosing activity A on the ith day. That's kind of annoying. This is for choosing activity B. And this is for choosing activity C on the ith day. And again, what's the difference between these transitions? Well, if you're going to choose activity if you're going to choose activity A on the ith day, then you can't have chosen activity B or activity C on the I-1 day, right? And similarly, if you're going to choose activity B on the ith day, you can't have chosen activity A or activity C on day I-1. And if you're going to choose activity C on the ith day, then you can't have chosen activity A or activity B on day I-1. And so finally, we're going to get values dp at n at 0, dp at n at 1, and dp at n at 2. And so we're just you're going to output the maximum between those. Oh, that's okay, so let's go ahead and submit this to make sure it's correct. Okay, and so that's that problem. Does anyone have any questions about how we solve this problem with DP? Okay, so I did put here bonus, how can we improve memory complexity? And so actually, yeah, does anyone have any ideas as to how we can improve our memory complexity here? So how can we take a less memory, or not even necessarily complexity, just I guess. Yeah, sure. You only need to store values for the previous day. Exactly. And in fact, you don't even need this A at I, B at I, C at I in a separate for loop, right? And so what you could actually do, and this idea is going to come up when we do knapsack as well, that if you only need values for a previous for one of the previous columns or rows, then you don't need to store all of them. And so instead, if we stored just dp at 3, or actually I might need 2 of them. Sure. And actually, I can just name A, B, C, and actually that would be a bit confusing. Never mind. So let's call this dp2 at 3. And so let's take an input of A, B, and C, just write in this for loop. And so instead of having this as our base case, we're going to have dp at 0, dp at 1, and dp at 2. Again, this is redundant because all of these will be initialized to 0 if you declare your arrays globally. So what we're going to update here is dp2, and we're going to update from dp. And instead of A of I, we have A. B and C. So we're going to have dp to store the previous day and dp2 to store the current day. So the reason I don't have just one dp value is if I change one of the dp values in the first line and then I try to use it again in the next line, I might have some problems if I need to reuse the same dp value. And so this should work fine though. If I just update my dp values, so dp at 0 is equal to dp2 at 0. Oh, I didn't change these. Whoops. Okay, and that should work as well, hopefully. Okay, so in this problem, it didn't really matter whether you conserve that amount of memory or not. I just wanted to introduce this idea of only storing the values that you actually need if you're running out of memory. Okay, so if there are no questions on this problem, we're going to move on to the next example. And so this will be the famous or well-known longest increasing subsequence problem. And so this says, given an array of integers, find the longest increasing subsequence. A subsequence is just a collection of numbers from the array. However, they must be in order. And so if our array was 1, 2, 5, 4, 3, 6, the longest increasing subsequence is either 1, 2, 5, 6, 1, 2, 4, 6, or 1, 2, 3, 6. And all of those would have length of 4, right? And so they're all valid longest increasing subsequences. And they said the numbers must be increasing, and so no two numbers can be equal. Okay, so we're going to let dp at I store the length of the longest increasing subsequence ending at this position, and so or ending at position I. And so what I mean by that is the last element of the subsequence should be A of I. And so for each element we go through, we're going to try to add it onto a subsequence that ended before it. And we can only do that if the last element of that subsequence we're trying to add to is smaller than the current element. And so what I mean by this is for every dp at I, I'm going to store the length. And for A at I is going to store all the elements. And so for any particular element, I'm going to go through whatever was before it. And if that element is smaller than my current element, then I can update my current element's dp value. And let's look at an example to better understand this. So if I had an array of 10, 9, 2, 5, 3, 7, 1, 0, 101, and 18. And our base case, okay, should label this as like 1 indexed. So what I mean by dp at 0 equals 0 is if I had no elements, just dp at 0 would be out of the array. So if you have no elements, you obviously have a subsequence of 0. Okay, and let's look at dp at 1, which refers to element 10. Okay, so 10 by itself, that's just one single element, and so that would just be written as a continuation of no elements, and so we're going to add on to the empty subsequence, so 1 plus 0 is 1. On dp at 2, same situation. I take 9, right? I look at whatever's before it, and I realize there's no subsequence that I can add to, and so my dp value for dp at 2 would still be the continuation onto the empty subsequence, which is dp at 0, and plus 1 is equal to 1. And the same thing with a 2. There's nothing before 2 that's smaller than 2. Now when we reach 5 here, which is dp at 4, and we look back at the numbers before 5, I see a 2. And so whatever subsequence that ended at 2, I can put a 5 after that subsequence, and that would be a valid increasing subsequence, right? And so I can say that dp at 4, which is the position of 5, is equal to dp at 3 plus 1. And the reason we add 1 here is because if we add an element onto an existing subsequence, we're gonna extend the length of that subsequence by 1, right? And so we're going to have dp at 4 to be equal to 2. And we can see why this is true. So recall that dp at I stores the length of the longest increasing subsequence ending at that position. And so if we look at the subsequences ending at 5, we see that 2, 5 is a subsequence, and that's going to have length 2. Hopefully that makes sense. And for dp at 5, that's going to be element 3. And we look back at all the numbers that are smaller than 3, and we'll find that 2 is the only one. And by a similar process as 5, dp at 5 is also going to be dp at 3 plus 1, because it's going to extend the subsequence ending at 2. And by the subsequences ending at 2, that's just 2, right? There's nothing before 2 that continues from it or continues to it. And when we look at 7, now we have more options. So if we look back at all these numbers before the 7, we have a 2, we have a 5, and we have a 3, and we can extend the subsequences of any of them. And so if I have, so we look at the dp values of, let's say, index 3, index 4, index 5. So for index 4, the dp value is 2. For index 5, the dp value is 2. But for dp 3, the index value is 1. So that's not very long. And since we want the longest increasing subsequence, we want to extend the sequence that is the longest, right? So out of 3, 4, 5, the longest subsequence leading up to that is 2. And so for 7, which is dp at 6, we're going to extend from dp at 5. Well, actually, it doesn't matter whether you extend from dp at 4 or dp at 5. And we're going to add 1 to it to extend to it. And so notice that I don't actually care about what elements are inside of the subsequence I'm extending. I only care about the length of it, because every time if I just have some random subsequence of numbers like 5, 7, 9, ... 100 or 1,000's fine, and I want to see if I can add 999 or 1001 to this subsequence, to this increasing subsequence, and see whether I can add to it and make the subsequence or make the sequence still increasing. Now, I don't care about anything that's before the 1,000, right? All that is going to be smaller than 1,000. So if my element is greater than this, that means I can put my element after that and I'll still have an increasing subsequence. Now, for the case of 999, it may be greater than anything that's before it, but it's not greater than 1,000. So therefore, it can't be extending a valid subsequence like that. But for 1,001, since this 1,001 is greater than the last element, it's going to be able to extend this increasing subsequence and form a new increasing subsequence, because anything before this 1,000 is going to be smaller than 1,000 and therefore smaller than 1,001. Okay, so moving on to DPS 7, which is this 101 here. So you realize that this can extend any subsequence it wants because it's greater than everything else before it. And so the largest out of 1, 2, 3, 4, 5, 6, that's going to be 3. And so 3 plus 1 is 4. And DP at 8, A at 8 is 18. And looking back at all the values, it can extend everything except for 101. And so it can again choose DP at 6 to extend and add 1 to the length, which gives 4. And so if we take the maximum among all of the 1, 1, 1, 2, 2, 3, 4, 4, we're going to get an answer of 4 for this particular array. And so the longest increasing subsequence of this array is 4. So let's go ahead and implement this solution. Oh, there's no sample input output. That's interesting. That's pretty rare. Anyways. So they said n goes up to 5,000. So I just like to have a bit of overhead. So I'm going to say 5,005. And for your DP array, you're going to declare it the same way because your I value only goes up to n, right? Okay, so why do I have caps on? I'm going to take an input of n and do I do it all in one? Nah, I won't. Okay, so we don't need this. We don't need to do this. We could just do this in one for loop, but I'll just separate it so it's clear. Okay, first of all, let's define our base case. Now, I don't actually need to say dp at 0 equals 0 because it's already initialized to 0. But just to form a habit of defining the base case, we're gonna do that because not initializing the base case is gonna cause you problems for a lot of other problems along the way. So yeah, anyways, we're going to implement our transition here. So remember what we were doing for each element. We were looking back and taking all the elements, all the indices for which the element was smaller than the current element and updating our DP value based on that. And so let's call this index j. And j is going to go from 0 because that's our base case. So continuing from 0, it would be the same as just having it at its own subsequence of length 1. And this j is going to be strictly smaller than I, right? You can't continue from a subsequence that's ahead of you. And so if a at j is smaller than a at I, then that means can extend from this element, or this element's from a subsequence ending at this or at a at j. Okay, and that means that dp at I is equal to the maximum between dp at I and dp at j plus 1. Okay, and for our answer, we want to take the maximum between all of them. And so I could make an answer variable and just update it, but just to keep things separate, I'll make an answer variable and then loop through all the values of the DP states and put answer is equal to maximum between answer and DP at I. I'm going to output answer. Okay, so they do have one example here. I guess I'll try that. 1, 2, 6, 1, 2, 5, 4, 3, 6. And I guess we can also put our own example in there. So 10, 9, 2, 5, 3, 7, 101, 18. I didn't put the number of elements, which is 1, 2, 3, 4, 5, 6, 7, 8. What did I do here? Oh, yeah, that would be a problem. Okay, and the answer was 4. And so I should explain, I guess I should point out which subsequences could form a length 4. So you can actually backtrack from this DP. So DP at 8, that stores an answer 4. So let's include the element at index 8. So that's 18. Obviously, you can also pick DP at 7 since that also gives 4. But yeah, it doesn't matter. So 18 would be the last element. And it took from DP at 6, right? So extended the subsequence that ended at the index 6. And index 6 happens to be 7. And so that's going to be our next element, or the second last element. And let's go back to DP at 6. That extended the subsequence from DP at 5. And so that would be the 3 value. And so the third last would be the element at A at 5. So that's 3. And if we go back to 3, if we go back to 5, that extended from 3, which is 2. So 2 will be the next element, and 2 extended from the empty subsequence. And so our subsequence in the end, one possible subsequence would be 2, 3, 7, 18, and that's going to be length 4, right? And obviously, there's also 2, 3, 7, 101. There's also 2, 5, 7, 101, and 2, 5, 7, 18. Etc., etc. Wait, no, I think those are the only 4. Yeah. So that would be an example of a longest increasing subsequence like that. And let me go ahead and submit this. Okay, so that passed. Does anyone have any questions about longest increasing subsequence, or any of the source code, or the base case state transition? Give me 1 minute, I'm gonna drink some water. Okay, well, if you have any questions, you can ask at any point. But if not, I think all of the code will be posted on GitHub later, hopefully. And yeah, we're going to move on to our next problem, which is longest common subsequence. So it gives us 2 sequences, the first one of length n, the second one of length m. Okay, this one doesn't give the problem statement, which is annoying. Let's do the other one. Okay, oh wait, no, this one's strings. Never mind. Okay, so the longest subsequence problem just says, given 2 sequences, you want to find the subsequence that is common to both, that is the longest. So for example, for this one, 1, 3 would be a subsequence of the first array, and 1, 3 would also be a subsequence of the second array. And so the longest common subsequence here would be 1, 3. And you know that there's a 1 3 2 and a 2 1 3, but that doesn't count because they have to be in order. And so that's what the longest common subsequence problem wants you to find. I wonder if this Wikipedia link explains it well. Yeah, it's kind of confusing. But anyways, yeah, it just wants you to find this subsequence that is common to both of these arrays that is the longest. Okay, so in our previous examples, we only had one array to deal with, but now that we have two arrays, we're going to need 2 dimensions at least, right? So for our state, we're going to have dp at ij store the length of the longest common prefix, or longest common subsequence in the prefix between the prefixes. Yeah, this is worded not good. And the prefixes a at 1 to I and b at 1 to j. So I think I should give an example of this. So if I had the array 5 3 1 4 3 4 2, okay, so 1 4 3 4 2. Oh, that's, and 2 1 3. Let's call this first array A and second array B, I guess. So our answer is going to be stored in dp at 5 at 3, right? So if we want, where's my document? Oh, here. dp at ij to store the length of the longest common subsequence in the prefixes. The prefix of A ending at I and the prefix of B ending at J. And so, for example, dp at, let's say, 4 2. That means that we'll be looking at the prefix 1 4 3 4 and the prefix of this 2 1, right? And so that would be the answer to this subproblem here. And so those are going to be the subproblems we'll be looking at. Okay, so for this problem, I think it would be a good idea to draw a table. But before that, let's try to plan out our transition a little bit. So if we have the length of the longest common sequences between 2 of the prefixes, and if we add to one of the sequences, it can't have a shorter longest common subsequence, right? So for example, if I had the sequence 1 3 2 and 1 2, we can see that the longest common sequences, or the longest common sequence between the 2 sequences, that's going to be 1 2, right? And whatever I add to this, say I add a 4 to this, or add a 12 to this, or -1 to this, that can only increase my subsequence. None of my original elements get changed. So it's going to be, whatever I add to it, the subproblem is still going to have the answer that's at least as good as 1 2. Right, so that means that dp at ij is at least as good as dp at I minus 1 at j and dp at I at j minus 1. Now, what if I had a at I equal to b at j? Now, let's say I had the sequence 1 3 2 4 and 1 2 4. And I wanted to find dp at 4 at 3. Now I know these two elements are equal, so a at 4 is equal to, and by the way, this is 1 indexing. A at 4 is equal to b at 3, where this sequence is a and this is b. Okay, so if these are equal, then that means they are added to this longest common subsequence of whatever this is. And so this is broken down into this smaller subproblem here. So if we take the longest common subsequence here, which is 1, 2, and we know that 4 is after is after 2 in both of these, then we can say that 1, 2, 4 is a valid common subsequence, right? Is there a mention? Oh, never mind, that's for juniors. Okay, so somehow that looks like a 6. I don't know how that happened. So, what was I saying? Yeah, so if these two elements are equal, then we break it down into a smaller problem where we take the longest common subsequence of the prefixes that come before these two elements, and we add 1 to it. So the length of 1, 2, that would be 2. And so 2 plus 1 would give us a longest common subsequence of length 3. And that is indeed our answer here, which is the length of 1, 2, 4. And now I think we can start making a table for this example here. So 1, 4, 3, 4, 2. And 2, 1, 3. So this is A, this is B. Okay, so actually I'm going to do I as the X and J as the Y, as the columns, I mean. When you're coding, it's not going to be the case, but it's just better fitted on this page here. Okay. So you guys get the idea. So this is 0, 1, 2, 3, 4. This is, I need another one. 5. This is 0, 1, 2, 3. Okay, so each of these cells, so if I had column 0, row 0, that's going to store dp at 0, 0. If I have column 4 and row 2, that's going to store dp at 4, 2. And so let's just visualize our table this way. So if you have an empty string with anything else, the longest common subsequence is going to be of length 0, because in one of your sequences you have no letters or no elements. So trivially, all of these with a 0 as its column or row are going to be 0. Okay, and let's look at dp at 1, 1. And so we look at element 1 and element 2. Are they equal? No. So that means we can't use the case where two elements are equal and we look at the subproblem excluding those two elements. And so, but what we do here is we use the fact that dp at ij is at least as good as dp at I minus 1 at j and dp at I at j minus 1. So we take the maximum between these two, but that's still 0. So dp at 1, 1 is 0. And continuing onwards, we have dp at 2 of 1. So we're looking at the prefix 1, 4, and we're looking at the prefix 2 in sequence B. And it's still, 4 is still not equal to 2, so we take the maximum of the thing above and the thing to the left, and until we reach element 5. So 3 is not equal to 2 and 4 is not equal to 2, but 2 is equal to 2. So for 5, we see that 2 and 2 are equal, and so excluding these, that would be these prefixes right here, right? And so let's look at the prefix 1434 to the empty prefix here. So that would be the prefix 40, right? So dp at 4 at 0, that would give us a dp value of 0. And so it's always going to be the one that's diagonally to the top left. And that's going to transition us we're going to be able to add 2 to the longest common subsequence of that prefix. And so that's going to be 1 here. And you can see that 1 is going to be greater than whatever is above and whatever's to the left. And that's where we're going to put as our DP value because we want the longest one. Okay, and let's do the next row the exact same way. So if we look at the prefix 2, 1, so for this entire row, we're going to be looking at this prefix here. So comparing 1 to 1, now that's actually equal, so we're going to look at the prefixes before them. So the empty prefix of A, that's going to be 0, and the prefix before the 1 here, that's going to be 2, so that's position 1. So that's DP at 0, 1, and 0, 1 is going to be 0. Again, it's the thing on the top left of the current cell, and we're going to add 1 to it to extend it. And 2, 2, so 4 is not equal to 1, 3 is not equal to 1, 4 is not equal to 1, and 2 is not equal to 1. So for the rest of the elements here, they're just going to take the maximum between whatever is above it and whatever is to the left of it. Again, because dp at ij is at least as good as dp at I minus 1 at j and dp at I at j minus 1. Because you can't add on to a subsequence and make the longest common subsequence shorter. So they're all going to be 1. And the maximum between two ones is still 1. Okay, so now let's look at the prefix of B, that is 2, 1, 3. So this entire array here. I don't know why that's so long. Yeah. Okay. So matching 3 with 1, those are not equal. So that will be the maximum between these two. Matching position 2, which is 4 to 3, that's still not equal. So that's going to give us the maximum as well. But if we look at the third elements here, we're going to see that these are equal. So we're going to look at the prefixes that's before them, right? So that's going to be the prefix 1, 4 and the prefix 2, 1. And that's going to be dp at 2 at 2. And so that's going to be this cell right here. Again, it's always the thing on the top left corner of the current cell. And so we're adding 1 to the dp value of the cell to the top left. We're going to end up with 2 here. And matching 3 with 4, that's not equal, so that's going to be a 2. And matching 2 with 3, that's not equal, that's still going to be a 2. And so our final answer here is going to be a 2. So are there any questions as to how we're constructing our dp table? Okay, well, if everyone understands this, I'm going to go and implement this. So, okay, so let's store the sequences in arrays as well as the dp table. Okay, so we have our maximum length to be 1,000. Actually, that's not necessary. We'll just put int a at 1005, b at 1005, and dp at 1005, 1005. So that's going to declare our dp array to be big enough because eventually we're going to have to reference dp at n at m, right? And n being the sequence, the length of the first sequence, and m being the length of the second sequence. So let's take an input. And let's take an input of the sequences. Yeah, let's make them 1 indexed. And the reason I have them 1 indexed is so I can have a base case that's empty. And obviously you could have a base case just as the first element because it wouldn't be too hard to compute. But yeah, that's kind of just preference. Okay, and for our base cases, anything containing 0 as a column or a row, that's all going to be 0, right? And again, I don't have to do this, but I'll just do it just to show that I'm declaring the base case. But your arrays that are declared globally will be filled with zeros if they're integer arrays anyways. So dp at 0 or dp at I at 0 is equal to 0. And for, okay, this is the base case. Now we loop to m, and dp at 0 at I is equal to 0. Oops, not 9. Okay, so now we can start to fill our dp table. Well, keep doing that. Okay, so we know that dp at I at j is at least as good as the maximum between dp at I minus 1 at j, because you can add on characters and have the longest common subsequence be shorter. So it's at least as good. Well, why are these in square brackets? Okay. Now if they're equal, so if a at I is equal to b at j, equal elements extend LCS of dp at I minus 1, j minus 1. So dp at I at j is equal to max dp at I at j, comma dp at I minus 1 at j minus 1 plus 1. And finally, we should output dp at nm. So dp at nm, again, where dp at ij stores the length of the longest common subsequence between the first I elements and the first I elements of the first sequence and the first j elements of the second sequence. So what dp at nm means is just the longest subsequence between the two entire sequences, right? Okay. Okay, so that's good. Are there any questions about this problem? Okay, if not, I think we can move on to, okay, so this is a very, very similar problem. Actually, they're both the longest common subsequence problem. I guess I can share the stock, why not? Okay. So, except this thing requires you to actually output the subsequence itself. And so if you want to go ahead and try this problem on your own afterwards, you're welcome to do that. For now, we're going to move on to the last example we have for today. Okay, so it says there are n children, numbered 1, 2, 3, all the way to n, and they have decided to share k candies among themselves. Here, for each I from 1 to n, inclusive, child I must receive between 0 and ai candies, and also no candies should be left over. Find the number of ways for them to share candies, modulo 10 to the 9 plus 7, and here, 2 ways are said to be different when there exists a child who receives a different number of candies. Okay, so if we attempt to have our state as dp at I stores the number of ways to share candies among j first what are they called? Oh, children. Then if we tried to transition from dp at I-1, which would be the number of ways to share candies among the first I-1 children, there would be a problem because we don't know how many candies they've already had in total, right? So we need a second dimension here so that we can transition effectively. So we're going to let dp at I at j store the number of ways to distribute j candies among the first I children. So now we know exactly how many candies they've distributed, as well as the prefix of children that shared this amount of candies. And the transition of dp at I at j would be the sum of dp at I-1 at k for every k between j minus ai and j. And so let's try to make sense of this. So if I had how should I explain this? So dp at I-1 at ways to distribute j candies among first I-1 children. And dp at I at let's use another variable k, ways to distribute k candies among first I children. And so if I transition from here to here, that means that the I child must have taken k minus j, right? And that's because if I added k minus j to j, I would end up having k. And so if I wanted to update dp at I at j, then the I child must have taken anywhere from 0 to ai candies, as stated in the problem here. Then that means that the first I-1 children must have taken either j minus ai candies, j minus ai plus 1 candies, all the way to j candies. And so in the case that the first I-1 children took j candies in total, then dp at I at j would add on the way in which the ith child took 0 candies, right? And for j minus ai, it would be the case where the ith child takes ai candies. And for j minus ai plus 1, that would be the case where the ith child took a1 minus 1 candies. And that auto-capitalized to make it confusing somehow. Okay, so if we were to implement the solution, actually I'm going to do that instead of hypothesizing. So I'm going to take an input of n. And because the number is very large, the problem tells us that we need to mod the answer by 10 to the 9 plus 7. But if you only do that at the end, you're going to overflow somewhere in between probably. And so you want to do that as you're going along, as you're going through the problem. I mean, so, okay, so A is going to store our values for the amount of candy each child can take. So let's take an input of that. And dp, so our base case is going to be already defined for us, so that's going to be 0. So the first zero children can share 0 candies in one way. So dp at 0 is going to be 1. And for the rest of our dp values, so for the value of I, which is the amount of children, the first I children, if the first I children took j candies, where j goes up to k, the first I children took j candies, then the I minus 1, the first I minus 1 children took between j minus a at I and j candies. And how does this make sense? Well, the ith child took either 0 or j minus 1 candies. Or, sorry, not either, between 0 and a at I candies. And so j minus 0 is equal to j, and so that would be maximum that the first I minus 1 children took. And j minus a at I, that would be the minimum that the first I minus 1 children took, right? And so that's why the first I minus 1 children took between j minus ai and j candies. Okay, so we're going to have to loop through from j minus ai to j, and I did not take input of k. Although this is probably improper to use k again. I'll use L. So we're gonna loop from j minus a at I. Now, one problem is j minus a at I might be negative, so we're gonna say maximum between 0 and j minus a of I. And that's gonna go upwards to j. And dp at I at j plus equals dp at I minus 1 at L. And so that that covers all the possibilities of the I child taking 0, 1, 2, 3, all the way to AI candies, right? And dp at I at j mod equals mod. And so this should work. Let's take in input. So our final answer is going to be stored in dp at n at k. So the number of ways the first n children can share k candies. What did I do? Oh, yeah, that's annoying. So it won't let me compare an integer with a long. It was all. So. Okay, you can see that it's correct, but for the big cases, it's going to TLE. And so even if we try to submit this, it's going to AC a couple cases, but it's going to TLE. And why is this? Well, if we analyze the time complexity of our solution, so we have a loop going through n, loop going through loop going through k, sorry. We have another loop inside, and so you realize that j minus a at I, that can go down to 0, and j can go up to k. And so potentially this loop can loop through O of j elements, right? And so our time complexity of this, that would be O of n times k times k. And so let's look at the constraints here. So if n goes up to 100 and k goes up to 10 to the 5, then O of n times k, that's going to be around 10 to the 2 plus 10, which is 12. And so that's going to be way too slow, right? Now realize that what we're actually doing here is we're just keeping, we're actually just doing a range sum query here. So what we're really doing is dp at I at j plus equals the sum of all the elements, sum of dp at I minus 1 at j minus a at I to dp at I minus 1 at j. Right, so we're essentially just summing up this range of values, and we can optimize this with prefix sum array, right? We know how to do a static range sum query in less than linear time. And so what we're going to do to our dp array is we're going to make it instead store the prefix sum leading up to dp at I at j, and so that we can transition an O of 1. Okay, so first of all, our base case is going to have to be different. So now everything after dp, we're going to construct our base case based on the prefix sum array. So j is equal to 0, or j is equal to 1, j is smaller than or equal to k plus plus j. We'll have dp at first 0 children for j candies. At j minus 1. Okay, so now this is going to be our prefix sum array for our base case. Now for our actual calculation of dp here, realize that if we want the sum of this range, how we use the dp array is that dp at I at j plus equals dp at I minus 1 at j minus the exclusive starting point, right? So that's dp at I minus j at the maximum between dp at, j minus a at I and 0, minus 1 here. Now the only problem is if this actually turns out to be 0, we don't want that to go into a negative value, and we don't have that defined anyways. So all we're going to say is how about if j minus a at I is smaller than or equal to 0, then we're going to return the value of 0. Otherwise, we're going to return the value of this. Okay, and instead of this for loop here, let's first mod this value. And now we're going to construct the prefix sum array as we go. So dp at I at j plus equals dp at I minus 1, or at I at j minus 1. So all of our columns are going to be a prefix sum array. And for our final answer, that's going to be dp at n at k, except this is a prefix sum array now that we've just constructed it, so we need to subtract by dp at n at k minus 1. And whenever you do subtraction with mods, make sure to add the mod and mod it again, just so you don't end up with a negative value, because C++ modding is weird. Okay, what did I do here? Oh, it doesn't like me comparing that. That's right. Okay. Okay, so that worked. Does anyone have any questions about this problem? Okay, so I guess if no one has questions. To summarize, we had a very bad time complexity because we had to have a quadratic factor with respect to k. But now that we've constructed a prefix summary on every dp value that we get in terms of the columns, every time we do a transition, it's going to be a constant time transition instead of a for loop. And that's because we built the prefix summary, right? And to retrieve our answer, we're just going to subtract k minus 1 to get the actual value of dp at n at k. And you might be new to this mod thing. So just whenever you do an operation, you should mod your answer by this mod so that you don't overflow. That's all there is to modding operations. Okay, all of this source code will be on GitHub at a later time today, hopefully. And if no one has any questions, this will be the end of the lesson. Try this problem if you want. I might post some problems later on in the day. And thank you for coming. Have a nice day.